So today is the last lecture day. So we will finish the spin wave analysis and magnetic excitations. Let's just finish the introduction to this magnetic properties of materials. Last time we talked about this paramagnetic susceptibility, and today we will continue describing the ferromagnetic properties and antiferromagnetic properties. So for ferromagnet, it is a special kinds of materials where there are some unpaired spins by Hahns rule, and then they coupled in a way that all the spins on the neighboring sides are parallel to each other. So in a Hamiltonian language, we can have such spin-spin interactions on the neighboring site, and this couplings Jij ferro is negative, so that when the spins on neighboring sides are parallel to each other, this energy is minimized. Okay, so this is the most stable state that we can find for particular ferromagnet, and the examples of such a ferromagnet include irons and cobalt and so on. So that's how we form a magnet. But the physics of this ferromagnet, we need to have this effective exchange field that is introduced to actually describe such a spin-spin ferromagnetic coupling. So this B exchange field is the effective, say, magnetic field or internal magnetic field, induced by the other spin moment nearby, acting on every side of the spin. So it looks like the system is actually made of individual spins. On top of that, you have a background internal magnetic field that is due to the spin-spin coupling of the neighboring sides, and this is called the Curie-Weisman field. Therefore, this so-called exchange field is actually proportional to the internal magnetization, and this is because of this kind of self-consistent picture of this ferromagnet, which induces spontaneous magnetization at low enough temperature. So that spontaneous magnetization could be described by so-called Curie-Weisman field, which is effective exchange magnetic field or exchange field. And you could calculate so-called this paramagnetic susceptibility at finite temperature or high enough temperature by the same way that we calculate this Curie law for a paramagnet, namely the magnetization is a function of this total magnetic field, which is the sum of this applied external field and the exchange field, which is the internal field. And this prefactor is precisely this Curie law, like spin susceptibility and chi p, and these relations could be manipulated in such a way that you could extract this chi p. By definition, this is the magnetization divided by the applied field, only the applied field. But the applied field is linearly proportional to this magnetization with a proper coefficient lambda, which is positive. As a result, you could rearrange this equation in such a way that chi p is given by this Curie-like law, but it's not exactly the Curie law. Only when t is above Tc do you see this 1 over T behavior. And so when temperature reaches Tc, you get sharp singularities of the spin susceptibility right at Tc. Okay, so this temperature is called Néel temperature or ordering temperature. So below Tc, the spins are ordered. Therefore, the susceptibility drops to zero because you cannot drive this magnetization by applying the small field because all the spins are locked by their neighboring spins. But at high enough temperature, when T is larger than Tc, you get exactly this paramagnetic Curie-Weiss law, because at high enough temperature, the spins are disordered, so they could point to any directions. Okay, so there's no preferred direction for the spins to orient it, and as a result, you get a Curie law. But this Curie law occurs only at high enough temperature, so that's ferromagnet. So this behavior could describe this iron, cobalt, and so on. And there is a very interesting another type of magnetic ordering, so-called antiferromagnetic ordering, where the spins on the neighboring sides go antiparallel to each other. So this is because, again, the spin exchange couplings between, say, side I and J on the neighboring spin shows a positive coupling constant J antiferro. As a result, the ground state configurations favors the spin such that all the spins are antiparalleled on the neighboring sides. So in such case, you can divide this system into two subclasses called sublattice. So you get sublattice A and B, but for each sublattice A and B, you get a perfect ferromagnet. Okay, so for example, the sublattice A, all the spins on A sides are pointing up, and all the sides on the B sides, all the spins on the B sides point down, or vice versa. But for each sublattice, the system looks exactly like a ferromagnet. Okay, so you could analyze this Curie-like behavior at finite temperature and also all the way down to zero temperature. You could follow the similar analysis as ferromagnet, but you should remember that this exchange field on sublattice A and B are actually opposite to each other, because the magnetization on sublattice A is the same size of MB with the minus sign. And therefore, you need to write down these two coupled equations which link this Curie-Weiss law and all this total magnetic field and magnetization and so on. And you could write down this two coupled equation, and when applied field is 0 and when t equals Tc, you get magnetization finite. And to solve for Tc, you need to find the eigenvalue of this 2x2 matrix. And if for this isotropic system where this prefactor Ca is the same as Cb, then you simply just get this mu c as your ordering temperature Tc. And you could calculate this antiferromagnetic spin susceptibility in the same way that we did for the ferromagnet, except that now you need to sum of these magnitudes of this magnetization on side A and side B and divided by this B applied. And if you actually do the algebra, you'll find that this is given by Curie-Weiss-like behavior, except now this denominator is T plus a parameter called theta, which is so-called nail temperature, or Tc. So instead of T minus Tc, you'll get T plus Tc. So that's for high temperature, but for low enough temperature, there are two cases that you need to separate. One is when B applied is actually parallel to Mn and Mb, which is this case. And in such a case, this change of internal energy due to this applied field is actually 0 because Ma plus Mb vanishes. In other words, so if your field is along the same or opposite direction of Mn and Mb, and you don't get any response. So chi-parallel is actually 0. This is at zero temperature limit. But of course, you get a different situation when this B applied is actually perpendicular to Ma and Mb in such a configurations. So suppose this is Ma and this is Mb, this is B applied. To minimize the energy, at least one of this magnetization vector will be tilted upwards until, towards the field direction, right? To minimize the energy, the Z energy. But you could consider that the tilted magnetization is just for, say, MB or for MA or for both MA and MB with equal amount of angle. So this is 2 phi as a tilted angle. And in such a case, the energy in that tilted orientation, when this B field is perpendicular to Mn and B, you get the following expression for the change of internal energy or Z energy. And you could find the optimal angle where this energy is minimized, and this angle is around B applied divided by 2 mu m. As a result, this susceptibility called chi perpendicular or transverse, which is defined as 2m phi divided by B applied, which is 1 over mu when t equals 0. As a result, you have two different behaviors depending on where the applied field is pointing to. So this is the susceptibility of a antiferromagnet, and this is the Curie law. High temperatures, but at low temperatures, there are two different curves. First, at high temperatures, this Curie law diverges or stops at a negative temperature, minus theta. Remember, this denominator vanishes when T goes to minus theta. Of course, T equals 0 is the lowest temperature we can reach, so it doesn't make sense to talk about this minus temperature. Okay? But if you extrapolate this Curie law to negative temperature, and right at T equals minus theta, you get this vanish of the denominator of the spin susceptibility. However, lower temperature from this Curie behavior, and you will find two different behaviors of a spin susceptibility. One is called chi-perpendicular, another is chi-parallel. So remember, chi-parallel vanishes as T goes 0, so the yellow curve actually goes 0 in the 0 temperature limit, but the red curve, which is the chi-perpendicular, goes to the positive finite value, which is 1 over mu. So, and this is what happens in the ferromagnet, such as transition metal oxide, manganese oxide, and cobalt oxide, and so on. Okay, so these materials show exactly this behavior that at high temperatures you get Curie law, but low temperature, depending on this field directions, it can go to the constant saturated value for chi-perpendicular, or directly goes 0 when the field is pointing to the same direction as magnetization. So finally, let me just introduce a very common magnetic properties called diamagnetic properties. So this follows the Lenz's law that you're already familiar. So when the flux through an electromagnetic circuit is suddenly changed, and the Lenz's law tells us that there is an induced diamagnetic current that goes against to the flux change. And the amount of opposite magnetization that is induced by the Lenz's law is given by this quantity over here, which is, for example, if you have ions in the center, but you have some electrons circulating around this ion core, and suppose you suddenly introduce a magnetic flux, and to actually cancel the flux change due to the introduction of this external magnetic flux, the system induces a spontaneous diamagnetic current which goes against the circulating electron orbit, and which produces the negative magnetization or magnetic moment that will cancel the flux change that you introduce to the system. And this effect is called diamagnetic properties, and which has the origin coming from the Lenz's law. And this happens to all the solid state material, that everybody is a diamagnetic, shows diamagnetic properties. But a superconductor, the BCS superconductor, is the perfect diamagnet because it repels all these external magnetic fields out of this superconductor. But for ordinary solid state materials, whether this is a metal or insulator or semiconductor or whatever, all the solid state materials shows certain degrees of diamagnetism. It's just how large is this fact. So for the long-range ferromagnetic or antiferromagnetic materials, this diamagnetic property is actually tiny. So you could forget about this tiny little bit, Lenz's law, and just look at this magnetization that is induced by this spin-spin coupling. But in the absence of this long-range magnetic order, and all the solid-state materials shows some degrees of diamagnetic response. Okay, so that's all I want to say for the introduction to this magnetic properties. So let's take a short break. When we come back, we will study the spin wave, a semi-classical treatment of the spin wave for ferromagnetic materials. So you could read the corresponding sections in all these reference books, such as Kittel's first book, or Ashker-Fermion. So this is just a phenomenology, but we will study quantum mechanical treatment of this low energy excitations above this magnetic order state. So let's talk about this so-called semi-classical treatment of a ferromagnet called spin wave theory. The spin excitations of this ferromagnet could be considered as a wave-like kind of a motion for a classical vector that undergoes some kind of oscillation. And let's just look at the ferromagnets. I mentioned their spin-spin coupling for these materials, and this coupling constant is negative, minus J, so that this minimal energy state is the state that all the spins are parallel. And you can consider this kind of a spin-spin coupling as an effective wide-spin field or exchange field. So you could decouple this neighboring spin-spin couplings on site I and J, where I and J are nearest neighbor, in such a way that you could define an effective wide-spin field. Okay, so the site J could be either I minus 1 or I plus 1 site, right? So if you look at for the fixed particular spin on site I, and we can forget about all these long distance couplings, but just look at this nearest neighbor coupling, that site I interacts only to the left and right nearest neighbor, so that this Si dotted into the sum of this Si plus 1 site and Si minus 1 site. But this Si plus 1 and Si minus 1 plays the same role as the Weiss exchange field, and you can define such a Weiss exchange field in such a way that this looks as if you have external or internal exchange field that comes from the neighboring spins but acting on site I. But site I is not a particular site, it can be any site. As a result, you can consider that the exchange field is kind of uniform, internal magnetic field that applies to all the sites, which comes from the spins on the neighboring sites through this so-called Heisenberg exchange coupling. And this is the origin of the B exchange, which comes from this neighboring spins. And when they interact with this particular spin on site I, this is effective way of looking at that. So the spin moment on site I could be further represented by this kind of a spin moment or magnetic moment mu I, and this Weissman field is a vector called Bi, so this mu dot B is called a Zeeman energy, okay, which follows this conventional definition of the Zeeman energy, which is the magnetic moment dotted the magnetic field. But what is this? Well, this in the classical EMN, this tells us that you get a torque, because if you take the Newton's second law, and you know that there's a magnetic moment coupled to the external magnetic field, and the system certainly shows a torque, right? And the torque is given by this, the time rate of the angular momentum. Okay, so h bar times Si vector is some kind of effective angular momentum, and you take the time derivative of that amount, which gives you a torque, because the torque is given by the time rate of the angular momentum. But what is the torque? The torque is nothing but mu cross B, right? From the classical mechanics. So you immediately see that you get equation motion for each individual spin vector, and then you could just decompose this kind of equation motion into, say, 3 directions. And suppose that this SZ is a spin quantization axis, where this is, the size of the spin is actually largely pointing to the Z direction. And this is much larger than this Sx and Sy, which is usually the case. When the spin is actually, moment is actually large enough, And remember, in your quantum mechanics, you have this picture that the spin is actually possessing around the z axis, which is the spin quantization axis, and where the z components of the spin angular momentum is the largest. And this is very similar to that picture, as you can see in just a moment, that if you write down this equation motion for the spin on site I, you get the 3 equation motion. So the third equation actually vanishes because the z component of spin angular momentum is conserved. It doesn't change. All right, so that solves this equation motion, and the solution is really simple, which depends on this eigenvalue problem. And this is your say oscillation frequency of this spin precession, and you can show that the spin vector actually is doing this precession where the x and y component of the spin vector lives on the circle, and the z component of angular momentum vector is constant. And this e to the I omega t represents this kind of a time oscillations of this spin vector around this z component of the spin angular momentum, and this kind of a precession frequency is given by omega, and omega is given by 2js times 1 minus cosine ka, where k is nothing but this wave number or momentum. And we will derive exactly the same so-called excitation spectrum in a pure quantum mechanical treatment. Here is just a semi-classical treatment of the spin wave. So you could consider the evolution of such a cone-like spin vector in time domain. And if you trace the trajectory of this spin vector from top view, and you will see that this shows a wave-like behavior. View on top of this cone, and you follow the spin vector, the endpoint of the spin vector on the circle, and you could trace out the wave-like motion of the spin vector. Something like this. Okay, so it goes like this. If you view this cone on top and the endpoint of the spin vector on the two-dimensional plane, and the circle will trace out as a kind of a oscillating curve, and the sinusoidal kind of oscillation, and it is due to the spin precession, so-called spin wave. Okay, so the spin wave analysis is a semi-classical treatment of motion of a spin vector under the influence of a Weiss-Wien field and for a ferromagnet. Okay. However, we know that this is just a classical view of a spin vector, because in quantum mechanics, for a single electron, you get either spin up or spin down. There's no way that the spin vector could actually go such a smooth wave-like oscillations, and in quantum mechanics, we call this spin flip. And the spin flip is a low energy excitations of a magnetic state. So in quantum regime, so we all talk about the spin flip because the single electron, when you have some external energy or injection of external energy or thermal energy, and the thing that the spin can do is actually go from up to down or down to up. So this kind of a spin flip process is actually the most fundamental objects at low temperatures, right? And you know that this the change of the spin angular momentum is actually plus or minus 1 if a single spin is flipped, because either go from plus 1 to minus 1 or from minus 1 to plus 1. But either case, the total change of the spin angular momentum is actually plus or minus h bar. Right? Okay, so such spin flip processes constitute fundamental, say, low energy excitations or magnetic excitations of a ferromagnet or antiferromagnet, and we will quantize this low energy spin flip excitations, and we call these excitations magnon, which again a quasi-particle, which is the fundamental object of a spin excitation of a ferromagnet or antiferromagnet. Okay, so let's take a short break. When we come back, we will continue using pure quantum mechanics to treat this ferromagnet and to derive the same dispersion. So for this case, you know very well that this, when momentum is actually small enough, or k times lattice constant is actually small, you can Taylor expand. So omega is actually some constant times k squared, because the leading term is actually 1, so 1 minus 1 is 0. So the next term is actually k squared if you Taylor expand this cosine term. So the dispersion goes like k squared. And we will derive such a quadratic, low energy excitations, spin excitations, and for a ferromagnet. Okay, so let's take a short break. So to use pure quantum mechanics to describe this ferromagnet, we need to go back to our earlier studies in quantum mechanics, namely the spin flip operator in simple harmonic oscillator, and the connection between the spin flip and the bosons. Okay, so we will introduce a special type of boson called Holstein-Primakoff bosons. And first, let's just review quantum mechanics. You know very well that for a single spin, say in harmonic oscillator problem, so we could define a spin raising and lowering operator, which is the linear combinations of Sx and Sy with the plus minus I coefficient. And this S plus operator is called spin raising operator, and minus is called spin lowering operator. You could very easily link this spin raising and lowering operator to the angular momentum states. So let me just illustrate this algebra, so you already learned that, right? So okay, so this can be checked in quantum mechanics. So if you raise a spin down state by applying S plus operator, you get h bar times spin up state. Likewise, if you lower the spin up state by applying S minus operator, you get h bar times spin down state. Okay, so and this is called spin raising lowering operator, which takes you from, say, this is plus 1/2 and minus 1/2. So go like this and like that. And you know very well from quantum mechanics that for a single spin, S plus and S minus operators satisfy this commutation relations, right? Okay, so this is well known, and this, I think you should be familiar with this commutation relations for spin raising and lowering operator, and also this algebra. So now this kind of a spin flip, operator looks very much like, the spin flip processes that I talk about. So either you flip the spin upwards or downward. This is exactly what happens when you do spin flip, right? So if you inject thermal energy to this spin order state, say ferromagnetic state, and spins are all pointing up, and then suddenly some spins get flipped into spin down state. And this process that goes from spin up to spin down state can be described by this S minus operator, right? And same with S plus operator. But this is just a review of your quantum mechanics and the connection between this, spin flip processes and the spin raising lowering operator. So now we will link this spin flip operation and these bosons. And in fact, the spin raising and lowering operators are nothing but bosonic operators. And you take this simple harmonic oscillator as an example, you know very well that the energy levels are equally spaced and are labeled by the quantum numbers and goes from 0, 1, 2, 3, 4, and so on. And the eigenvalues or eigenenergies of the simple harmonic oscillator goes like 1/2 h bar omega as a ground state energy, and then 1/2 plus 1 h bar omega, and 1/2 plus 2 h bar omega, and so on and so forth. So when you go from one level to the next higher level, you actually increase this m by 1, and eigenvalue is actually 1 h bar more than the previous state. But if you look at just this, a subset of this energy level diagram of the simple harmonic oscillator, if you just look at n equals 0 and n equals 1 states, and you can compare this energy level diagram with the spin, and you will know immediately the connection between these two. So you can define this two states as spin minus 1/2 h bar state or plus h bar over 2 state, and this for the spin down state, you can attach this n, which is n quantum number for harmonic oscillator problem, which is say n equals 1, and for the spin up state, you could actually consider this as n equals 0 state. So if you just look at these two cases, then there is a one-to-one correspondence between this harmonic oscillator problem and the spin 1/2 problem, right? Great. Then you know very well that if you would like to go upstairs for the simple harmonic oscillators, you could define a dagger operator, which allows you to go from, say, the ground floor to the first floor, and so on and so forth. And if you want to go downstairs, you should apply A, right? A is the Hermitian conjugate operator with respect to the A dagger, and you know very well that the A and A dagger corresponds to this. A dagger corresponds to the creation of a single boson, and A corresponds to destruction of a boson, right? So we already defined that in this phonon section. Okay, and if you look at these two diagrams, you know immediately that the spin flip can be formulated in terms of the boson, because if you go upstairs, you actually create a spin flip downwards. So in any case, you could identify this S up minus plus operator as this raising and lowering operator in the harmonic oscillator problem. And you know very well this harmonic oscillator problem, this A and A dagger corresponds to the boson operators. And as a result, this S plus and S minus can also be formulated in terms of the boson language. So this very important message is here is that the S plus, S minus operator is actually bosonic. And this is our starting point. We should define this bosonic representation of the spin racing lowering operator in a ferromagnet. And this is precisely what this Holstein-Primakoff approach is doing, which is another way to link the boson operators to the spin flip. So let's just introduce the Holstein-Primakoff approach. As I mentioned, this S plus and minus is given, but this is the Holstein-Primakoff boson definition, S minus. Okay, so this says that this plus operator is defined as h bar times the square root of this thing. Inside the square root is 2s minus this mb, occupation for bosons. mb is b dagger b, and 2s is actually 1 if s is actually 1/2. But this s is the size of the spin, could be equal to 1/2 or larger than 1/2. But this approach is valid for large spin. And remember, the square root is actually an operator because mb is b dagger b. It's not a number, but an operator. Okay, so this is the complicated operator. At the end of the day, we will make some approximations about the square root. But the square root is needed because you need to conserve this commutation relations. So for S minus, it's actually this Hermitian conjugate of this operator, and therefore the b dagger comes first and then the square root. As z is nothing but the z components of the spin, which is a difference between the size of spin and the number of boson. And the number of boson in our language is actually the number of spin flips. So we will see in just a moment that this correspondence. Okay, so if you have a single spin flip, then you have boson number, which is 1. And if you have 2 spin flips, and this boson number should be 2, and so on. And because this boson satisfies this commutation rules, and this guarantee, this kind of definition guarantee that this S plus and S minus satisfies the commutation relations. Also it has Z, S plus minus. And therefore this definition actually is a valid definition because they are consistent. Okay, this boson satisfies bosonic commutation relations, and the spin satisfies the spin angular momentum commutation relations, right? And if you use this definition and you guarantee that this angular momentum commutation relations are satisfied. So, and this Holstein-Primakoff approach is valid if the spin is large, because large S expansion is justified if the number of bosons is actually very small compared to this 2s, which means that this spin flip processes take only a minor role, and which will not destroy this magnetic order at low enough temperatures. But we'll see later that depending on dimensionality of this ferromagnet, a lower dimension, meaning a one-dimensional and two-dimensional ferromagnet, this kind of spin flip processes will dominate at low temperatures, which destroy the magnetic long-range order and suppress this ferromagnet. Okay, so let's take a short break. When we come back, we will use this Holstein-Primakoff approach and to analyze the ferromagnet. Okay, so let's plug in this Holstein-Primakoff representation for the spin racing lowering operator and express this Heisenberg ferromagnetic Hamiltonian in terms of this Holstein-Primakoff bosons. And for this SI dot Sj operator, this you know very well from quantum mechanics that this could be decomposed into this Si plus Sj minus Sj minus Si minus Sj plus, and divided by 2, and plus this Z interactions, right? and S plus and minus actually Sx plus minus I Sy. This S plus is actually square root times B, and S minus is B dagger times square root. And then you could pull out these factors to S in the square root, and then you could just combine this Bi dagger and Bj and insert it by these two square roots. When this number of bosons is actually small compared to the size of the spin, and you could Taylor expand this square root, and you could forget about this square root at the lowest order approximation. That square root is actually 1, okay? Because this mb divided by 2s is too small, okay? So you could go higher order to pick up this non-trivial corrections, but at zeroth order, forget about this. You also get this ni plus nj operator times spin, and also ni nj term, which we will neglect as well. And you expand this square root, and you get this lowest non-trivial contributions to the Hamiltonian, which consists of the constant, which is s squared times magnitude of the j times the number of sides, and the coordinator number, the number of neighbors. So in one-dimensional problem, you have two neighbors, right, left and right. In 2D square lattice, you get 4 neighbors, right, up, down, left, and right. In 3-dimensional cubic lattice, you get 6 neighbors, right? So Z is called coordination number, or number of neighbors. And the second term is called H1, which is our focus, and higher order term is hidden in H2. So H1 is exactly this quadratic form, B dagger B, by summing over momentum K, and you get, this called dispersion omega K, or say a bosonic excitation frequency. And H2 is higher order term, which consists of many boson operators. And we know that this bosonic operator describes the spin flip. If the spin flip number is actually small, and this consists just a higher order contributions, and we could forget about this at this point. And we look at this H1 term and plus the constant term. And we know very well that this boson operator in momentum space is given by this Fourier transformation of a Bi on real space lattice, and this omega k is given by number here with a prefactor times 1 minus 1 over z times the sum over this Fourier phase on the neighboring sides. This j refers to the neighboring sides. In one dimension, this j refers to the left and right side of this particular side I, and xi and xj are coordinates of this site. Okay, so if you sum over these two exponentials, you get precisely this cosine term, e to the ika plus e to the minus ika divided by 2. This is for 1D, and this is precisely this cosine ka. And gamma k is cosine ka in one dimension. And you Taylor expand this cosine, 1 minus cosine term, you get k squared dependence. That is precisely the dispersion or low energy excitations of a ferromagnet. So remember, this is, to be precise, this is the cosine function. So you get a minima at k equals 0, but maximum at minus plus pi of k, and you get quadratic dispersion. So remember, this is ferro. All right, so we solved most of the problems of ferromagnetic, say, spin wave theory. Low energy excitations above the spin, this ferromagnetic ground state is this form that you create a spin flip bosons. So number of spin flip equals the number of bosons here. And the boson number is carried by h bar omega k, which describes the low energy excitation energies above the ground state. So this is called Holstein-Primakoff theory of a spin wave analysis. Great. And we could estimate the corrections of this magnetization due to the spin flip processes. So let me just make some cartoon diagrams. So suppose I have a ferromagnet at 0 temperature, but at finite temperatures, some spins, say this spin and that spin, are flipped. And you know that there are 2 spin flips, then this MB is actually 2, right? And the remaining SZ, which is the Z component of the spin angular momentum, is the total spin, right? Minus, the number of spin flip. So this capital S refers to the size of the spin, the total spin, which is 1/2 h bar times the number of sides, right? So if all spins are pointing up, then the total spin is actually what n times 1/2 h bar, right? Okay, for this n sides system. But if you have 2 spin flips, then effectively you need to subtract this number of h bar, because each spin flip you actually lose 1 h bar, because plus 1/2 h bar, and this is minus 1/2 h bar, so altogether you lose 1 h bar. So if you have 2 spin flips, then you lose 2 h bar of your total spin angular momentum along the z-axis. And this is the way that you could estimate the loss of your total spin angular momentum by spin flip processes, right? And therefore the number of spin flips is the same as the number of bosons, Holstein-Primakoff bosons. And you can keep track of the total spin angular momentum by keeping track of this number of spin flips and number of bosons. Okay, so this is the very elegant way of studying this effect of spin excitations of a quantum ferromagnet by spin flip. Okay, so let's just calculate this corrections of a total magnetization of a ferromagnet due to the spin flips, and this delta M0 refers to this number of boson. You know very well that number of bosons satisfy this Bose factor, right? Bose h bar omega k divided by kBT. Okay, so number of bosons satisfy this Bose distribution function. So in other words, this magnetization corrections due to spin flip could be evaluated by simply just evaluating this number of bosons. And the number of bosons satisfies Bose factor. So it is very easy to estimate these corrections, and let's just do the algebra. This momentum reaches some cutoff, you may run into some trouble. Okay, so this lower bound of this momentum is called the infrared cutoff, K0, which corresponds to the 1 over your length scale. Okay, the system size, 1 over your system size. And you know very well that when K is actually very, very small and omega K is actually K squared dispersion, and there's some trouble. Because when K goes 0, and this will actually become 1, and 1 minus 1 is actually 0 in the denominator, you get some kind of a BEC. But it's not a BEC condensate, but you get some trouble. You get some singularities because the denominator vanishes. As a result, we need a cutoff, and the natural cutoff is the length scale. The 1 over the length scale is actually the minimum of this K0 momentum, which we call the K0, but up to some K bar, you can consider this omega K is a very, very small excitation energy, which is a quadratic dependent on this K, and you could use this Taylor expansion to actually expand this exponential factor, which means that when this omega K bar or below K bar, this omega is actually much less than this thermal energy, okay, or H bar omega is much smaller than this thermal energy, and then you could Taylor expand this. So when this omega divided by t is very, very small, then you could tail expand that. And you could separate this integral into, the small momentum region and the large momentum region. When k is larger than k bar, then you don't have such a pure k squared dispersion. Instead, you need to something else. But we don't care about this. This is finite. So the leading term that will lead to some large contributions is this, the first term. The leading order term, or the dominant factor, is the first small momentum sum. That part gives you the leading contributions. And we should Taylor expand this exponential factor up to linear in omega over t, and that's how you get this factor omega over t. And omega is given by zjsk squared, quadratic dispersion, and we get this integral. And we will analyze this on the first integral more closely in just a moment, and we'll see some singularities going on here. Okay, so let's take a short break. And this is precisely what I meant earlier, that depending on the dimensionality of your system, and these corrections due to the spin flip could dramatically change the ground state, okay, from the ordered state to the spin disordered state. And you will see precisely what I mean by that if you evaluate this integral as small momentum region, and you'll find that for 1 dimension and 2 dimensions, and this correction actually diverges at ground state as t goes 0, so that there will be no magnetic long-range order at any given temperature in 1-dimensional ferromagnet, and also the long-range order in 2D ferromagnet occurs only at 0 temperature. Okay, so this is called a very important theorem called the Merman-Wagner theorem. So let's just look at this first integral where you can do Taylor expansion. So at any given temperature, finite temperature, and the statement is that this the first integral diverges as the system goes to infinity, or in the thermodynamic limit, where 1 over L system size inverse is actually 0, or system size goes infinity in 1D and 2D. So let's just look at this result. So you need to show that for a ferromagnet, at finite temperatures for 1-dimensional and 2-dimensional systems, as the system goes infinity, the size of the system goes infinity, and its correction due to spin flip is given by this result here, where little t is the reduced temperatures, t temperature divided by j times size of the spin, and omega is quadratic in k with a prefactor capital D. So in 1D, this divergence or singularities goes like 1 over k0. So this is like 1 over k0. When k0 goes 0, this goes infinity. In 2D, this divergence is a log divergence. It's log k0 goes to 0. It's log 0. So the log 0 is different from this 1 over k0 divergence, as you know from your calculus. And this is called the Merman-Wagner theorem, saying that for 1D and 2D system with magnetic long-range order, such as this ferromagnetic properties materials, and there's no magnetic long-range order because the delta m0 is actually minus infinity at any given finite temperature, which means that your net spin moment is actually S total minus this delta m0 magnitude, which goes to 0 already. So you know very well that before this delta m0 goes to infinity, this negative contributions to the magnetization or spin moment will cancel out exactly the S total from the beginning. So you don't allow this. This is just estimation from this, simple naive Holstein-Primakoff approach, that before this delta m0 diverges, it cancels exactly S total, and therefore the perfect, alignment among all the spins are gone. Instead, any given temperature, the spins are disordered. So if you take the average of the spin moment on every site, you get 0. This is because besides the spin flip processes dominate a low energy excitations of a one-dimensional and two-dimensional ferromagnet, so that the spin flip processes destroyed coherent long-range order of the spin angular momentum. However, for 3-dimension, things are different. In 3D, we do have a magnetic long-range order at finite temperature, and you could estimate this delta M0 for 3D. Sum over e to the minus n k squared over t, and this is some special function called Riemann zeta function, and this Riemann zeta function is defined as, and as a result, delta M0 for 3-dimensional systems goes like t to the 3/2. And this is a very important result because this is checked by experiments. So experimentally, this behavior has been confirmed for a ferromagnet. So delta mt divided by m0, 0 minus t divided by m0 is given by SQ 0.0587 kBt over 2js 3/2. And Q is actually 1, 2, and 4. It is Z, number of nearest neighbors. And you could see all the experimental plots from the textbooks that this delta M, which is the correction of magnetization at any temperature divided by 0 temperature magnetization of a ferromagnet versus t to the power of 3/2 goes like a straight line. So the different slope refers to different this coupling constant and different coordinations and different prefactor and so on. But this behavior is really robust and has been observed experimentally. So let me summarize this ferromagnetic excitations at low temperatures and low energies. Limit this excitation spectrums goes like k squared. It's a quadratic dispersion. As a result, you could calculate this corrections to the magnetizations, and you show that at 1 and 2 dimension limit, and when the system size goes to infinity, you got exact cancellations of your spin moment, which tells you that perfect long-range order of a ferromagnetic type is fully suppressed. Instead, you got random spin flip processes going on. So I guess that's enough for this magnetic properties. So of course there is the antiferromagnetic low-energy excitations, but we don't have time to study. If you are interested, you could read our corresponding chapters.